Welcome to the section, Scaling Data. In the previous section, we created visuals from our data. During that process, we manually calculated various scales to figure out where to place our visuals on the screen and what sizes to use and also what colors. In this section, we will learn how to use several of the built-in scaling and mapping techniques in D3.js. Using these will help us greatly simplify our code by not having to do manual calculations like we did earlier to position, size, and color our elements. In the first video, we will look at how scales help us map data to our visualization, and we will examine several of the different types of scales available within D3.js. Using what we learned about scales, we'll then apply linear scales to create our visuals. We will use these linear scales to calculate the x and y positions and also the radius of our bubbles. While we do this, we will see how using these scales simplifies our code as compared to performing manual calculations. In the third and final video of this section, we will modify our code to use Ordinal Scales and D3.js color schemes to select the colors of our bubbles. So let's jump in and start learning about scales. Welcome to the first video of this section, an overview of scales. In this video, we're going to learn all about D3.js scales, what they are, and why we should use them in our code. Scales greatly facilitate us in converting data from its original domain values into those needed for creating data visualizations. We will learn how to use these scales to convert things like fertility rate, life expectancy, and population into positions in our visualization, as well as size of our bubbles. To understand how to use scales in this manner, we'll need to understand the concepts of domain and range. Domains tell D3.js what our data looks like in its original source, and the range tells it how to convert those values into those that are useful for our data visualization. We'll cover many of the different types of scales provided by D3.js, and we'll look at code examples of various linear and ordinal scales. The purpose of scales is to convert values in your data into values that are useful for creating a data visualization. The values in your data are referred to as the domain values. Domain values generally never have a direct mapping into what you need to represent them in a visual. Scales give us the ability to convert those domain values into range values. Range values will often represent things such as the x and y position, size of elements, and the colors. Scales in D3.js are actually JavaScript functions that are created by D3.js factory functions to provide a specific domain to range value mapping. The graph on this slide demonstrates a linear scale. The input domain has values which have extents of 100 and 500. The output range has extents of 10 and 350. A linear scale, using these domain and range extents, will map the value of 100 from the domain into 10 in the output range and 500 to 350 in that output range. Using the input domain and output range extents, the linear scale will be able to convert any values from the input domain to the output range. As an example here, 300 would be converted to 180. Linear scales often get used to convert domain values into positions along the x-axis or y-axis of a visualization. And we will see this in operation when we convert our life expectancy and fertility rates into positions on our axes. D3.js comes with quite a few different types of scales. These scales can be generally broken down into four large categories. The continuous scales apply a function to your input values and return a new output value. They're a lot like standard mathematical functions that you'll see, such as y equals f of x. They are continuous because you can pass in any real numbers, and the result will also be a real number. The possible values are not discrete and can range from negative infinity to positive infinity, and with any decimal points. Another common type of D3.js scale are the ordinal scales. Ordinal scales map a discrete set of input values to a discrete set of output values. A very common use of ordinal scales is mapping values to colors. This is demonstrated here by this quick picture of mapping these letters into a different color for each letter. Another type of scale are the sequential scales. Sequential scales are similar to continuous scales, as you can pass in any rational values into those scales. The difference being that the output values generally map to be between 0.0 and 1.0. Using these scales, you may not actually see these output numeric values, as they are then processed into other categories such as a color blend that's demonstrated here that goes between purple and green from 0.0 to 1.0. Quantized scales take a continuous set of input values and convert them into one or more categories of output values. An example demonstrated here converts our values into 3 different bins of colors: red, orange, and blue. If values are less than 0, then they'll be red. If they're between 0 and 1.0, they'll be orange. If they're greater than 1, they'll be blue. So why do scales exist and why should we use them? We use them because they give us a simple way of converting domain values into various characteristics of our data visualization, such as position, size, color, and in the case of animations, velocity. So enough theory. Let's hop into some code and learn about scales. Okay, let's learn about some D3.js scales. I have opened the index.html file from the begin folder of 1.3.1. This code sets up a baseline for us to demonstrate the application of different scales to different data sets. There's a div in here named ID equals div1 that we'll use to create HTML, which will show us the input values versus the output values of our scales. We will use the data variable to represent our input data, and we'll use the scale variable to assign the various different functions to use to scale that data. The selection code down at the bottom just finds our div and then adds a new div for every data item, and then sets the text inside of that div to just be a string representing the actual value that we passed in, plus the application of the scale to that data value. And right now, let's hop on over into the browser to see the output from the base code we have here. And you can see we actually don't have any output. That's because the data array inside of our code is an empty array right now. So let's change that to have some values, such as 0, 1, 2, and 3. Back in the browser, we can see now that we have 2 columns of data, 0 and 0, through 3 and 3. This is just really an identity function here defined for scale. So all it is returning the same value that's passed in. Let's change that to be a D3 scale function. One that's identical to what we just did. It's D3.scaleIdentity. Going back in the browser here, we see we have the same output. That's because this function is an identity function. Whatever you pass in comes back out. Now let's see another useful D3 function called D3.range. This generates a sequence of numbers. So I'm going to call D3.range, passing it 10. Flipping back to the browser, we can see this generated a sequence of numbers from 0 through 9. This function has other forms. For example, let's do 0, 10, 2, which will start at 0, increment by 2, and stop short of 10. So we got 0, 2, 4, 6, and 8. So let's change this to generate 0 through 10. So that would be 0, 11, 1. And there we go. We have 0 through 10. Now let's change our scale identity to a scale linear. And heading back into the browser, we see this hasn't changed from before. That's because just using a scale linear like this just creates a one-to-one mapping. It's basically an identity. So what we want to do to make this useful is add a call to .domain and pass it in some domain extents. This needs to be an array of 2 values. So let's pass in d3.min of our data and d3.max of our data. And let's hop back into the browser. And this mapped our values 0 through 10 to 0 through 1. This mapping occurred because we did not define a range. So it defaulted to values between 0 and 1. To specify the range, we just chain on a call to .range and to give it the 2 values that we want to map at the low and high. So going back in our browser, we see that this didn't change from before, kind of proving that this set by default the range to 0, 1. The gist of what's going on here is that the low value in the domain gets mapped to the low value in the range. So this will be 0 to 0 in this case, and the high value of the domain gets mapped to the high value in the range. In this case, 10 gets mapped to 1. The intermediate values get linearly interpolated between the low range value and the high range value, hence the linear scale. The practical part of this is in mapping domain values into positions in your visual. Range 0, 1 doesn't necessarily provide this, but let's say our visual is 800 pixels wide. If we do 0 to 800, then this automatically goes and does that mapping. You can see here that our values at the low end got mapped to 0, which would be the left side of the visual on the x-axis, and 10 got mapped to 800, which would be the rightmost side of our x-axis in our visual. This is awesome because by just using these two function calls, we've eliminated a lot of tricky calculations inside of our application. And as we will see, this helps out with other things such as margins, which would make regular calculations kind of complex. But let's say we just want a left margin in this a few pixels, say 50, and a right margin, then we would just do 50 through 750, and everything's handled automatically for it. So we go back here into our browser, and we can see now that our data value of 0 got mapped to 50, and our high end to 750. And let's look at how if we change the range. Let's say we want the range to go from 30 through 120, or 119 this would be. We go back to the browser, we can see how this has handled all that intricacy for us automatically. So what these scales do, it allows us to clean up our selection code and keep those kind of in terms of our domain data. And it gives us a way of declaratively specifying how these translations should occur and without having to worry about all the intricate mathematics. So let's look at a different type of scale now, the power scale. So let's change our range to be between 0 and 1 inclusive and stepping by 0.1. And then let's change our range to be between 0 and 1. This is a good demonstration for power scales. Now going back to the browser, we can see this is just incrementing by 0.1 every time. It's still using a linear scale, and you can see some of the JavaScript artifacts about rounding and dividing floating point numbers, but we'll have to just deal with that. So now let's change scale linear to scale pow, and go take a look at this in the browser. So we still have the same output here because by default the power scale uses an exponent of 1. So let's change that exponent. We do that by adding a call to .exponent, and let's set it to 2. Back in the browser we can see now that this has now gone and squared all the input values. So 0.1 becomes 0.001, 0.9 is 0.81. So every value being passed in is basically being squared. It's being applied an exponent of 2. So let's change our exponent of 2 to 0.5 and see how this changed our output. So what we see here right now is our resulting value from our scale. Essentially, if you take the square root of that value, you'll result with the original value. So if you multiply the value on the right by itself, we get the input value. A scale pow with an exponent of 0.5 is equivalent to using a square root. So scale sqrt. And going back into the browser, we'll see that we have the same output values as we had in the previous example. Now let's look at using a logarithmic scale. We use a logarithmic scale by using scale log, and this will help us scale down our exponential data into a more linear fashion. So let's change our data here to a set of fixed values that are exponential in nature. So 10, 100, 1,000, 10,000, and 100,000. And we'll keep our domain the same to pick up the min and max of that. But let's change our range a little bit. Let's change that up to 100. So in the browser here, we can see we had 10 mapped to 0, 100,000 to 100. And then we used a logarithm to essentially come up with a linear interpolation of those values logarithmically across the intermediate points inside between 0 and 100, which is great. We've now converted our exponential data into a linear format. I'd like to show one variant of the linear scale, known as a time scale. Time scales solve a fairly common and difficult problem in data visualization, and to be honest, in data manipulation in general. That problem is, given two dates representing an interval of time, where do I position other dates on the screen, such as along an axis, at fixed intervals? A good example of this is an axis with two dates on the ends and wanting to put a tick mark at every day in between. To do this, we're going to use a linear scale. So let's change back to scale linear. To demonstrate, let's change our domain to be two dates. We'll start with 2017, January 1st, and we'll go for a week here to 2017, January 7th, or as our domain extent. And let's change our range here from 0 to 800. Like we had an x-axis, it's 800 pixels long. Then let's change our data to a single element array representing a date where we want to figure out where would we place that along that axis. So let's say 2017, January 3rd. Going back into our browser here, we can see that the value that we got out of this is 266.66 indefinite. So basically 1/3 of the way. That date is 1/3 in between the 1st and the 7th. And we can do this for multiple dates. So let's come in here and let's add another one. So let's say 2017, January 5th. And go see what this looks like in the browser. And there you can go. That one would be at 533 1/3 pixels over from the left. I don't know about you. I think that's pretty cool. Our last example of scales will be of an ordinal scale, which map discrete inputs to discrete outputs. So let's change our scale from linear to ordinal. Let's change our domain back to using our data variable instead of these dates. And let's assign to data a few strings in a list. Start with A, then B, then C, and D. And let's make our range into a discrete set of values. Let's make this an array of 1, 2, 3, and 4. And one last small change. Let's change our domain not to be just data, but D3.set, so the unique values in our data. Then let's head back into the browser, and we can see now that we mapped A to 1, B to 2, C to 3, and D to 4. So let's go back into the code, and let's add another data item. We'll call it E. So what happens in this case? We now have a scenario where we have more data items than range values. Let's go back to the browser, see what happened. So we can see here that E got set to 1. So what goes on here is that if you have more data items than range values, it repeats back to the beginning of the range. This is actually pretty important with regards to handling overflow and doing things like mapping colors to values in your data. This is important because many times we'll use built-in D3.js constructs to select colors. And this leads into something I want to show you called color scheme. So let's do a console.log, and then let's put in here D3.scheme category 10, and go see what this looks like in the browser. So let's hop back over to the browser, and on our console output, we can see we have this output here, which that scheme category 10 is an array of 10 distinct predefined colors that come in D3.js. This is neat because D3.js comes with a number of built-in color palettes that we can use for our data. So let's go back into the code and change this so that we can see these colors in action. So let's add a variable named scheme and set it equal to D3.scheme category 10. Then let's change our data to be equal to D3.range from 0 to scheme.length plus 1 and by 1. So let's change our domain to be our data, and our range is going to be our scheme variable, which will map all our data items into our color scheme. And let's hop back to the browser, and we can see our output value is now we have a mapping of each of our integer values into a color code. And because we had 11 distinct data values, number 10 here wrapped around to the first color. So let's go to our code and change this to actually use these colors. So let's scroll down here, and we're going to chain on to our append for the div, a call to .attr, and we're going to set the style attribute. And we're going to use a function here to get our datum, and we're going to return from that color : plus our scale, passing in our data item. There we go. And heading over to the browser, we can see here that we're now got our text is set to the colors in that color map. Now this is pretty cool because we didn't have to sit there and figure out what the mapping is between our distinct data values and a made up set of colors for those. Now let's go back to our code. There's more color schemes than just category 10. There's also a category 20. True to its name, category 20 is a 20 color palette. There are other variants of category 20. Another is 20B, which is a different color set. And there's 20C, yet another color set. So this is a real valuable time saver in D3.js. These really help us be able to map data into colors without putting much effort into it. And we'll see this in more detail in the third video in this section when we map our regions data into a category 10 data set. Okay, we've gone through looking at creating a number of different types of D3.js scales. D3.js is really rich in the types of scales that it has, and we've really only touched the surface. But I think we've got a good example of what we need to use for this course.